Okay, so introduction to chapter 17. We're going to start with buffers, and all the other parts are already up for this chapter. So buffer solutions, what are they? How are they useful? What's the point? So basically a buffer solution is simply usually a weak acid and its conjugate base. Your blood is the most common thing you've probably learned about so far about buffer systems. So when we talk about your blood, we talk about it having a buffer, or being a buffer system, where you have carbonic acid and a carbonate ion in solution. So the whole idea is that if your pH rises or drops, or an acid or a base is introduced into a system, if the acid is introduced into the system, then the conjugate base will neutralize it. And if a base is introduced to the system, the the weak acid will neutralize it. Typically, when we talk about buffers and neutralizing, the whole purpose is to maintain a certain pH. So we're talking about maintaining some pH. And if last time you were in a lab, you might have noticed that with our equipment, that's supposed to be an H, you might have noticed that some of our equipment, we have these little bottles that we stick probes into, and that's for the purpose of calibrating our equipment when it comes to titration. When we can calibrate the equipment, then what's happening is we're picking usually a buffer mixture of about 4 and also 10. So that's able to give the probes a good reading of what we're looking for. So our buffer system, whether it's acidic or basic, it's going to be in order to maintain a certain pH of a solution. So when we have an acidic buffer, that's going to be our most common one. It's going to contain our weak acid and its conjugate base, which is going to be the anion of that weak acid. Now, the most common one you're going to see is acetic acid, and usually sodium acetate. Now, sodium acetate is going to break up into its individual ions, and it's the acetate anion that's going to be doing the work of neutralization. We don't really care about the sodium. The sodium is just kind of there, but it doesn't do any work. It doesn't react with anything. You can think of it kind of like a spectator ion, okay? And when the sodium acetate is in solution, and they break up into their individual ions, into the sodium ion and the acetate anion. If, for example, sodium hydroxide was introduced into solution, that also, because it's a strong base, will break up into its sodium ion and hydroxide anion. And in this case, this anion is not going to do anything. It's going to be the acetic acid that goes ahead and neutralizes that hydroxide anion. So what happens when we add small amounts of strong base or strong acid to a buffer solution? Well, the long and short is that if a base is added, then the acid component of the buffer is going to neutralize it, and we're going to form water, okay, from this hydrogen and this hydroxide. If an acid is added, then the sodium acetate is going to come in, and it's this acetate anion, because remember they break up into their ions. The acetate anion will neutralize the hydrogen from the hydrochloric acid, for example, and we will get acetic acid in solution and then sodium chloride. The sodium from the sodium acetate and the chloride from the hydrochloric acid. When we add a base, the pH will rise slightly. When we add an acid, the pH will lower slightly. And when I say rise and lower, I mean numerically, because we know the closer to 1, the more acidic it is, the closer to 14, the more basic it is. So again, this is just going over how it works. So we can think of Le Chatelier again, where if we're already at equilibrium, meaning the forward and reverse reactions are equal, and there's a disturbance to the system, meaning I've added an acid or I've added a base, then we're going to have to come to a new equilibrium. It's not going back to the old equilibrium, it's establishing kind of a new normal, if you will. So let's look at how we would calculate the pH of a buffer solution. When you calculate the pH of a buffer solution, we're going to use very similar strategy to when we just had Kc and Kp. Still products over reactants. Still can use the exasmol approximation when we have a small enough Ka. So far we've had Kc, Kp. Now we're going to have Ka and Kb, which we've already introduced with the acid-base portion of this. And again, the K is just a constant. The A and the B indicate an acid or a base. So if I have 0.1 molar acetic acid and 0.1 molar sodium acetate, in my ICE table, I'm starting off initially with both of these. Nothing is added, no acid or base is added. So what is the pH of this buffer solution? I have negligible amount of acid here. Remember, H3O plus and H plus indicate protons are added and therefore an acid is present. So once I have my initial starting amount, there's going to be a change by X. The acetic acid is going to get used up. The acetate anion is going to increase. And I'm going to form an H3O plus because, again, we're talking about this as being an aqueous solution. So that means it's understood that it's in water. Water is already present. That the H2O did not come from any magical place. It didn't just poof appear, okay? So we're talking about an aqueous solution. So that means water. And then once this forms an anion, this hydrogen comes off and gets added here to form that H3O plus. So at equilibrium, I have 0.1 molar minus the change. I have my X formed and then X added. Because we're talking about acetic acid, the Ka for that is 1.8 times 10 to the minus 5. Okay, that just is. You can look on any chart. For purposes of a test, your Ka, assuming you're not solving for it, will be given in the problem. For homework and purposes of that, you're most likely just going to have to look it up in your textbook or Google or something like that. But once we get to the minus 5 power, we can generally say it's small enough, further enough away from the number 1, to make that exasmol approximation, which means we can cancel out this plus and minus X. So now all we're left with is X times 0.1 divided by 0.1. This 0.1 divided by 0.1 cancels out. So what we can say is that the change, X, is equal to the Ka when the concentrations of the weak acid and conjugate base are equal. So when the weak acid and conjugate base concentrations are equal, we can say that the change is equal to the Ka. Finding the pH from that is just simply saying, okay, negative log of the hydrogen ion concentration. Remember, we're just solving for X. Okay, X is the change, and that's going to give us the value of the concentration of the hydrogen ion concentration in solution. Once we take that negative log, we're going to find that the pH is 4.74. So go ahead and try this one on your own. And now you're going to find that, again with acetic acid and sodium acetate, that the exasmol approximation works. So now what you should see is that the 1.8 times 10 to the minus 5 is going to be equal to X times 0.100, whole thing divided by 0.200. So that's 1/2. And solving for X, we can say, okay, 1.8 times 10 to the minus 5 times 0.2 divided by 0.1. So what we're going to say is X is equal to 3.6 times 10 to the minus 5. That is our change. So it is also our hydrogen ion concentration. So we're just going to take the negative log of the 3.6 times 10 to the minus 5. And that's going to be a pH of 4.44. And that should make sense because we have a higher concentration of acid in our solution. Now let's talk about the Henderson-Hasselbalch equation. When you see the word buffer, you need to be thinking Henderson-Hasselbalch. 9 times out of 10, we can exclusively use that. It is critically important that you understand, though, you can only use the Henderson-Hasselbalch equation when the X is small approximation works. So meaning a really small Ka or Kb. Okay? If you can't use the X is small approximation, you're not only going to need an ice table, but probably also the quadratic equation as well. So this is just a way to solve for the pH, where we have pH is equal to the pKa, which we can derive from the Ka. If you recall, the pKa is equal to the negative log of the Ka, plus the log of the concentration of the conjugate base divided by the concentration of the weak acid. So you don't have to worry about how it was derived. If you want to go through and do this math, you can. Just the takeaway is this equation right here. That is your Henderson-Hasselbalch equation, and it comes about because of all the log rules that are associated with doing the math. So how do we find the pH? Well, we can use the ice table or Henderson-Hasselbalch. Either one is just fine, so long as the exasmol approximation is valid. As long as it's valid, then either one works just fine. I don't care which one you pick, so long as you're doing the correct math and everything is working appropriately. So let's look at this. Calculate the pH of a buffer solution that is 0.050 molar in benzoic acid and 0.15 molar in sodium benzoate. So notice we got our benzoic acid right here and the benzoate anion because this will break apart. And remember, sodium doesn't play a role in any of this. It doesn't play a role in any of it because sodium won't neutralize anything. So we're only looking at the key players. You can almost think of sodium as a spectator ion. So if we were to compare and contrast the ice table versus Henderson-Hasselbalch. Here is your ice table right there. We started off with 0.05 molar of the benzoic acid, 0.150 molar of the benzoate anion. We have a change in X, change in X, change in X. Our Ka is really small, so we can make that X a small approximation. So we would simply say 6.5 times 10 to the minus 5 is going to be equal to X times 0.150, because we're making that X a small approximation, so we can pretend those are gone. Whole thing divided by 0.050. Okay, now if we do that math, we're going to get X is equal to 2.2 times 10 to the minus 5. Okay, so we take the negative log of that. And I get 4.66. Using Henderson-Hasselbalch, I'm solving for the pKa by taking the negative log of the Ka and then plus the log of the conjugate base divided by the weak acid. Add these two together, lo and behold, 4.66. The Henderson-Hasselbalch approach is honestly much more simple. You just have to remember it's the concentration of the base over the acid. It doesn't matter if your buffer is an acidic buffer or a basic buffer. It's always the base over the acid, unlike where normal K is products over reactants. You're going to see that becomes important when we talk about a basic buffer. So this one, there was all sorts of, the problem was written out here, and I don't know what happened to it. It's just gone. But this is the work associated with it. So if you go to example 17.2 in your book, you can see the rest of it. Okay, again, I don't want to get too repetitive. When adding an acid or a base to a buffer solution, what happens? It should make sense that if you add an acid, even though it's going to maintain a certain pH, it's going to become more acidic. And if you add a base, it's going to become more basic. If you remember a titration curve with no buffer, you're going to see something like that. A titration curve with a buffer, you're going to see a much longer S. And of course, I've exaggerated my S slightly. But the reason for that is because in here, this is where all the buffering is happening. It's maintaining a certain pH. Yes, it's rising slightly, but not like here. And it eventually exceeds the amount of buffer that's present and shoots up quickly or downwardly quickly in, once your buffer is used up. So how do we determine the pH of a buffer solution after adding an acid or a base? Well, first we have to do some stoichiometry. That's number one. And then equilibrium calculation. That could mean Henderson-Hasselbalch, but again, you got to make sure the exosmol approximation works. And equilibrium calculation just means ice table. So let's take a look. You're starting off with a 1 liter buffer solution that contains 0.1 moles of acetic acid and 0.1 moles of sodium acetate. Now, we just did the problem where we had equal moles, right? And we found out that the pH was equal to the negative log of the Ka, or in other words, X, the change. So, but what happens once we add an acid? So let's just look at how we look at this, okay? So you'll notice now that we're in moles. If you remember from acid-base titrations that the equivalence point was where the moles of the acid equaled the moles of the base. That didn't mean volume was equal, but that meant the number of moles was equal. And what that means is at the equivalence point, when the moles of the acid are equal to the moles of the base, then you have neutralization, pH of 7. So now we're still in moles because we have to consider the moles that are present and the moles that are used up and the moles of everything to see what's used, what's added, what's created, etc. So when we start this, in the very beginning, this does kind of look like an ice table, and we are kind of going to sort of treat it like an ice table. So what you'll notice is that before the addition, I have no hydroxide, I have no base added. I do have 0.1 moles of my acetic acid, and I do have 0.1 moles of my acetate anion. Then we're going to add 0.010 moles of the base. That will all get neutralized by the acid. So what that means is 0.010 moles of the acetic acid is used up. That also means if it's used up, this is neutralizing that. So that means I've added now 0.010 moles of the acetate anion. So there's my change, minus X plus X. I'm starting off now with 0.09 because 0.010 was used. And I have now 0.110 moles. Now they've made this very easy for you. We are back to molarity here. But because it's 1 liter, it's super simple. The molarity is going to be equal to that of whatever the moles are, right? So 0.09 moles per 1 liter is 0.09 molarity, molar. So then we have our change. It's acetic acid, so we can make the excess small approximation. So now we're left with 1.8 times 10 to the minus 5, which is the Ka, equals X times the new concentration of the conjugate base and the new concentration of the acetic acid, the weak acid. When you solve for X, which is the hydrogen ion concentration, you're going to get 1.47 times 10 to the minus 5 molar. We're simply going to take the negative log of that, and we see it's 4.83. This is compared to 4.74, which was our original when we had equal starting amounts and no base or acid was added. Okay, so part 1 is finding the change in moles, and then part 2 is converting to molarity and doing an ice table, and then plugging and chugging into your Ka equation, products over reactants. Again, this is just showing you how if you had used the Henderson-Hasselbalch, you would have had to do the mole change first. You can see that they got the mole change difference, plug and chug, and you wind up with the same number. Again, I don't care which way you do it. You can do it whatever your little heart desires. So long as, if you're using Henderson-Hasselbalch, the excess small approximation is valid. That is the most important part. It will not work if the extra small approximation does not apply. So when we talk about basic buffers, their job is to do the same thing, where it's to buffer for a higher pH because we don't want to exceed that higher pH. Typically, most basic buffers range around the pH of 10 mark. But it all is still exactly the same mathematically, where it's products over reactants and base over acid. Couple of takeaways. You need to remember this, where Ka times Kb equals Kw, but Kw is 1.0 times 10 to the minus 14. You don't have to worry about this derivation, but you should also know that the pKa and the pKb equal 14, just like the pH plus the pOH also equal 14. You can go ahead and work through this. This is example 17.4 in your book. It's a really good one to practice. You might see it in the future. Wink, wink. Buffering range versus buffering capacity. So the range is just that. It is a range. What is the pH range that the buffer is going to buffer for? For acetic acid, the most common one, the most common range is roughly about 4.65 to about 5.2. That's if we want to keep a pH in that range. Buffering capacity just simply means the more amount or the higher concentration of the weak acid and its conjugate base, or the weak base and its conjugate acid that you have, means it can neutralize more stuff that's added. That should just make sense. The more that's there, the more it can neutralize. How do we solve for the buffering range? Simply by saying, okay, what's the lowest pH we want and the highest pH we want, then figuring out mathematically what the effective range is based on whatever it is we're using for our concentrations. So sometimes it's a little bit of playing with numbers. One of the labs you would have done had you been seated was creating a buffer to buffer for a pH. Your target pH was 4.85. And that's playing around with concentration of the acetic acid and the sodium acetate. I think we also have salicylic acid. That's a choice that you can use. And there was another one, might have been benzoic. I can't remember off the top of my head right now. But the thing is, you kind of play around with the concentrations of each, and you can mathematically solve for it depending on what it is that you want. You know, what is that target goal of a buffered pH? So when will they be most effective? First and foremost, equal concentrations. That's number one. Number two, when you have a 0.1 base versus 10 concentration of acid. So that ratio is important. And most effective when you have a higher concentration of acid and a base as opposed to a lower concentration of an acid and a base. It should make sense that the more concentrated something is, the more it can buffer, because the more entities are present in order to neutralize out an acid or a base that's added to the system. This is just, again, preparing a buffer. How would you choose to get the best, most effective buffer solution at a targeted pH? Well, again, it's using Henderson-Hasselbalch. We're assuming all of these are weak enough that the exasmol approximation works, and that, you know, you can go ahead and use Henderson-Hasselbalch. So if you were to go ahead and say, okay, they just started with formic acid. So you're told the pKa, they plugged it in. You know your target pH is 4.25 simply because they gave that to you. And you know you want this whole term to be equal to whatever this algebraically turns out to be. In this case, 0.51. So when you do the math, you just got to remember your log functions. If I have log of the base over the acid, then I can say the base over the acid is equal to 10 times 0.51, the power of 0.51, and that's going to be 3.24. So once you have that, you can see that, you know, this is going to be your, maybe your best bet, maybe not. Maybe the nitrous acid would be better. But the pKa in this particular case does lie closest to the pH that you want. So I would maybe take the time, like once you pick one, I would maybe take the time and compare it to this, because those pKa's are pretty close. But if you have a smaller, numerically smaller pKa, you would expect to see a different Ka. So maybe just compare and contrast those. You can definitely rule out the chlorous and hypochlorous because their pKa's are too wildly off. That's it for the intro for Chapter 17 and buffers. All other parts of Chapter 17 are up.